Welcome back to week 9 of Introduction to Meteorology. This is a forecasting methods chapter and content, and this is kind of the pivot point in our semester where we stop talking so much about physical processes and the relationship of pressure to wind and the relationship of temperature and humidity to energy, and we stop talking about physics and thermodynamics and we start talking about weather or climate or air pollution or all this stuff that kind of matters in meteorology. So this is kind of that nice transition point at the beginning of the middle of the semester where we can do this. And so in our book and in our content and pretty much in our minds this week are what are the tools and data that forecasters use, how do they use them, and what are some of the methods that they employ, and on top of all that, talk a little bit about our map assignment for this week. So it's pretty uneventful week. It's a nice week if you're kind of a how do they do that, what goes into it. This is a fun week, and the content at the end of the chapter is honestly pretty cool, where he kind of walks through city by city and kind of goes through the process, different methods, different forecasting approaches on kind of the same case. Pretty cool way that the book does that. So starting with data and tools, he identifies 4 major types of data sources, and that's he mentions ASOS, which is the main part, but not all of the surface observing that goes on. These are weather stations that report usually every 20 minutes. They're literally at airports around the country. They're near the runways. You might see them even when you're taxiing down the runway. They measure wind, they measure temperature, pressure, precipitation, all the variables that you see on the news. So he mentions ASOS by name. There's actually several of these automated networks, but they all pretty much work in the same general kind of way. Stick a weather station out there, take care of it, make sure it's happy and accurate, and let it report data nonstop around the clock. And then another thing he mentions are radiosondes, which are weather balloons, and these are literally a bucket of instruments that is tethered to a big hot air, or not hot air, but a helium or hydrogen balloon, and they launch these twice a day at certain places around the country, and that balloon carries those instruments up in the atmosphere, and they measure temperature and humidity as it goes up, and they track the motion of the balloon as it goes up, and that helps them estimate wind. So not a real technologically advanced way of doing things, but the best and most accurate way that we have to measure the condition of the vertical structure of the atmosphere. Absolutely irreplaceable, super important on severe weather days, super important on winter precip days where the precipitation type may be uncertain. In fact, it's so critical during severe weather days and winter precipitation days that sometimes they'll spend the extra several $100 and launch an extra sounding in the middle of the day because it's just that dang important. So those two are called in situ measurement types. That means the instrument is actually in the stuff that it's measuring. In situ is Latin for something like in the place, in the situation. I don't know exactly what it means, but what it means in observing is it's in the soup. In situ means it's in the soup, and then the other methods are remote sensing, which measure the soup from a distance. So those are radar and satellite. Remote sensing, that means the instrumentation is actually separated physically from the junk that it's measuring. In a radar is fixed to the ground and it rotates and it observes a big area around it, 100 miles, a couple 100 miles or so. And that's all one instrument, and it's sweeping around. You see the fake little sweeping lines on the news. Those aren't real, but they, that's pretty much how it works. So that's one way, and that's really critical in a severe weather situation, and it helps spot boundaries and developing storms and all that stuff. And then satellites, of course, are way up in the atmosphere. They're orbiting the Earth. He makes a distinction between geostationary satellites and polar orbiting satellites. And they do a fantastic job of filling in the gaps in all the places in the world that aren't directly observed by weather stations. So satellites have their own set of issues, but they provide a wonderful and gorgeous kind of big picture thing. Geostationary satellites sit over the same place on the Earth, and they orbit around the Earth and kind of stay trained on the same area. And they're great for the kind of big picture monitoring function. And then there's polar orbiting satellites, which are a lower orbit for what that's worth, and they orbit from pole to pole, and the Earth kind of spins around underneath them, and so they eventually take this low orbit picture in a banded kind of way around the Earth. And they're really good for looking at details of like developing hurricanes and all of that. So that those are the main types of observation streams. There's in situ data, which means the probe is actually in the situation, in the soup, and there's remotely sensed data, which means the measuring device is physically removed, but it's still giving you information about what's going on in a place. Then he gets into some kind of stuff specific to the Weather Service and some of their information platforms, and honestly, I'm not going to test on AWIPS, but it's a nice read. Then he talks quite a bit about, starts talking about numerical weather prediction. And numerical weather prediction is essentially computer modeling, where a computer or set of computers are programmed to represent the physics and dynamics of what we understand in the atmosphere. So the really complex kind of mathematical version of what we went through earlier in the semester, which is, how is pressure related to wind, and how much moisture can that transport, and what are the physical processes of evaporation. All that physics and stuff is built into these weather models, and it literally from grid point to 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 grid point is calculating what are those conditions. What, for whatever grid point that you live on the map, or whatever grid point you live nearby, it's calculating for every, say, 5 or 10 minutes, what's the temperature there, what's the humidity there, what's the pressure there, and how's it related to its neighboring grid points, and how are they feeding into each other. And it's a really complex process, and it has come a long, long way, even in just the 20 years or so that I've been around meteorology. Made huge strides, and now computer models are pretty much the de facto universal first guess that forecasters will use. So I want to be careful in the way I say this, because it is the first tool that many forecasters look at. What does the computer model say about the next 6 hours or the next 24, 72 hours? But the computer models aren't perfect. So while they may do a great job of describing the big picture meteorology, they're great at pushing big pieces around. Like, where's the low pressure going to be? Where's the big high pressure area going to be? In general, what are the big picture winds going to be like at upper levels? They're very good at that. In fact, they're massively beneficial at that. But they're not so good at some of the subtle things in weather, which are, how is this tiny shallow layer of cold air at the surface going to be pushed around by all these features? Turns out that that's a situation where a tiny layer of cold air at the surface, if it gets pushed a little farther, it can make the difference between a warm, sunny, cold, overcast day, or rain versus freezing rain. And it's that little sliver of air that the models don't handle very well is a pretty critical forecasting situation. So he emphasizes, and I'll support, that computer modeling is a huge tool that forecasters of all kinds use. But no forecaster worth her or his salt is going to rely on the computer to make the forecast. In the end, forecast comes from a forecaster who invests his skills and reputation and education and experience into taking responsibility for that forecast. So don't want to downplay the role that computer modeling has made, because it's really improved the batting average of forecasts, especially those kind of 1 to 7 day forecasts. But shouldn't overdo it either, because there's a lot that they can't do very well, and other tools like the forecaster's brain are used to fill in the gaps in those. So he goes, and he also spends a big part of the chapter, an amazingly large part of the chapter, describing kind of the things that can go wrong from one forecast to the next. Pretty much boils down to observations aren't perfect, computer modeling isn't perfect, our understanding of the physics isn't entirely perfect, and these errors in a big complex system, these imperfections, can kind of grow and feed into each other and kind of orbit out of control after just a few days. So in a lot of times, depending on who you want to get in an argument with, anywhere from 6 to 10 days is kind of the upper limit to the kind of reality of a weather forecast. They really diverge from reality, and they definitely diverge from each other after about a week, give or take a few days. And it has to do with, calculating the exact weather conditions at every grid point on the map and every grid point up in the atmosphere above each one of those grid points. You're just not going to get it exactly right, and the more those errors kind of multiply, and you just kind of crash and burn away from reality. So he talks about chaos, and he also talks about the process of when they do diverge from each other. It's a pretty good indicator that the predictability from that point forward for any of the models is probably pretty suspect. And you may have to resort to some of your other tools. All right, so what are some of those techniques? Well, he dives in and he kind of arranges them from the most primitive to the more sophisticated and recent, and then, of course, the numerical weather prediction that we just talked about is the most modern kind of culmination of all we know about computers and physics and all of that. But he does this nice kind of historical look at different techniques that have been used in the past and still are used in places, in certain situations today. And the most primitive kind of ancient technique is the persistence forecast, which is whatever's going on right now, that's what's going to happen in the future. So if it's raining now, it's going to rain in the future. As he notes, that breaks down after not a long time. The next is a steady state forecast, and that's pretty much the features that we see on the map are moving at a certain speed and direction, and we're just going to extrapolate that out into the future and make our forecast based on where we expect those features to be. And that's not used a lot anymore, hardly at all, in the big picture forecast. But you see that a lot in severe weather situations when they kind of cut into programming, and you'll see a lot of information like, we expect this storm to be in town A. Well, I'll go back to my Oklahoma roots. We expect this storm to be in Piedmont at 8:11. And then in Edmond at 8:17, and then in Chandler at 8:31. And where they get that is a good old-fashioned steady-state forecast that makes kind of three assumptions. One is that, first of all, they've identified the feature, but the first assumption is we know what direction this thing is moving. Two is we know accurately what speed it's moving, and three is that nothing will change to alter either one of those. And in reality, none of those assumptions is ultimately perfect. You may have an idea of what speed and direction the thing is moving, but the reality is you're not going to hit all three of those all the time. So it's a great tool. It's a great heads-up tool. It's a great ballpark tool. All else being equal, assuming we kind of identified the speed and direction correctly and that nothing will change, this storm should be on your doorstep in 14 minutes. It's not a bad way to go about things, but it's also not gospel. So don't bet the farm on it being exactly 14 minutes, and don't be surprised if it's 11 or 19 or if the storm's changed during that 14 minutes. So that's an example of a steady state forecast, and it still has a pretty useful application in how storms move across the map. The next kind of family of forecast techniques that he goes into are kind of all variations on that analog technique. And what the analog technique is, we saw this situation in the past and it produced this outcome. Therefore, if we see this situation again, it will produce this outcome. And then the kind of a little more evolved version of that, he calls it a statistical method, which is like, we've seen this configuration or something like it, whether the oceans and atmosphere have certain characteristics, several times in the past, and a certain percentage of that time it produced this particular kind of outcome. So we're going to lean towards that kind of outcome in our forecast. And where you see elements of this are in the kind of seasonal forecasting, what's going to happen in the spring, what's going to happen next summer, what's going to happen 2 months from now. And I should point out that this isn't the only, they use a lot of tools and they're amazing people and forecasters, but one element of what they use in particular related to El Nino or La Nina. So for example, it's February 2012 and we're in the midst of a pretty long-standing La Nina event, which is cold water in certain parts of the Pacific. And it turns out that in an established La Nina during the cold season, that kind of tips the scales towards warmer, drier winters in most of the U.S. Doesn't happen all the time. It doesn't bat 1,000. It's definitely not a 100% kind of thing. But when we see La Nina in the cold season in the United States, that means more often than usual, the outcomes have been warmer, drier winters. And lo and behold, this winter of 2011 and 12 has been doggone warm and dry as well. So, the big storyline in a lot of parts of the country, where's the snow, where's the snow, where's the snow? Well, it's not just warm. It's also, there hadn't been a lot of precipitation falling. And this winter will go down as a warm, dry winter, which will kind of reinforce that statistical relationship that La Ninas, tend to produce warmer, drier winters more often than when we don't have La Ninas. So that's an example of an element of the seasonal forecasting that they would lean on. So then he talks about kind of the wording of forecasts and talks about the time scales of forecasts, like from a nowcast to a long range or climatological forecast. And then he goes back to accuracy and skill, and this is kind of how it's measured. And then he gets this kind of fun, what you can do locally if you observe conditions in your backyard, kind of a rule of thumb forecasting techniques, works 2 out of 3 times kind of way of going about these. And then he does a really cool section on a forecast for 6 cities, and he kind of dabbles in a few of these forecasting techniques, and he tracks conditions at the surface, and you see a lot of surface maps. And then you see on a really, pay attention to that 500 millibar map of figure 9.21. 500 millibar is often called the upper air, upper atmosphere, and it can have a lot to do with what's going on, and that'll pay off in a future map assignment. Finally, the map assignment is about air masses, and you'll draw a lot on Chapter 8 in this. And it's another map of the great state of Oklahoma, and it is deals with air mass types. So you'll see 3 distinct regimes in this map of Oklahoma. It'll either be warmer or colder relatively in a part of the state. It'll be moister or drier based on the dew point. And you also get some wind information. And so the trick to the assignment is back to that maritime, tropical, continental, polar stuff that we did. Maritime being moist, continental being dry or from a land source, tropical being warm or from the south, polar being cold or from the poles, from the north in the United States. So the combination of where the winds are kind of coming from and knowing just a little bit about the geography of the United States. There is a big body of water southeast of Oklahoma called the Gulf of Mexico that can really contribute to conditions there. And so that might be something to think about, where it's warm and moist and the general winds in certain parts of the state, and knowing where the Gulf of Mexico is. If that's a source region, that's probably going to contribute a lot to warm and moist air. And so it's a map assignment basically of knowing your geography, knowing your sources. Air masses are kind of like people. We tend to take on the characteristics of where we hang out. And so if an air mass has been hanging out over the Gulf of Mexico, it's going to acquire those characteristics, and it's going to become warm and moist. And then eventually the atmosphere will push it somewhere. And when the winds carry that air to a place, it will carry those characteristics along with it. So when you get winds from the general direction of a warm ocean, it's typically going to be warm and moist. If you get winds from the direction of Canada, it's going to be cold and dry. So that's the gist of that assignment. Good luck this week. If you have any questions, send me an email or a message or ask on the forums, and have a great week. And this world is better because you're in it.